Okay, so this is a flash introduction to our poster by Michael Schlesinger, who's also here, and me. So you know a lot about submodular functions. I'll speak about submodular function minimization, as Francis did. Assume that we have a function. Okay, I come from computer vision, we have a slightly different history of submodularity than machine learning people. So the terminology is somewhat different. So in computer vision, we tend to call such functions energy function. So I have a so-called energy function of many discrete variables called E, and it's decomposable in terms of what Francis said. So it's a sum of functions, each depending on a subset of variables. So here's an example for variables. Typically, the total number of variables is huge, like 1 million, whereas the number of variables each cost function depends on is small, like 2, 3, 5. I don't assume submodularity yet. So this is a purely combinatorial optimization, but it has a interpretation in statistical sense. So it's equivalent to maximum posterior inference in graphical models or Markov random fields. If I plug in this energy function to this formula, I get what is called Gibbs distribution defined by a graphical model, and then finding the mode of this distribution is equivalent to minimizing this energy function. This is trivial. This has a lot of application like vision, speech analysis, bioinformatics, economics, and so on. This is clear. So this thing, so far I don't assume these cost functions are submodular. But this thing, of course it's NP hard, this problem of this minimizing energy function of discrete variables, it's NP hard, but it has a very nice LP relaxation. And you get this LP relaxation or linear programming relaxation, you get this relaxation by combining two components. One is a lower bound, concave piecewise linear lower bound on the minimal energy, or piecewise affine, and you get this lower bound simply by swapping minimization and summation. So this is the true minimal energy, and this is the lower bound. So this is very easy. And also obvious. And the other component is so-called, we call it reparameterizations or equivalent transformations of the energy function. It turns out that if you take the energy function and you add some, for example, unary function to some cost functions and subtract the same functions from other cost functions, such that these unary functions cancel out, then you get the same energy function, but the little cost functions are different. So you have certain freedom in how to, in what these little cost functions can be, and still the total function is the same. So you have this freedom, and if you combine these two things, it's obvious that you can maximize the lower bound by over all possible reparameterizations. And this can be written as an LP relaxation. Actually, it is a dual form of a very natural LP relaxation of the original problem. This is often used in computer vision and somewhere else, and many algorithms have been proposed to solve this LP. Of course, you can't solve it by off-the-shelf algorithm like simplex method because it's huge. Various algorithms have been proposed to solve large instances of this. And now, I said that energy minimization is NP hard, but we know that tractable subclass is if the cost functions are submodular. And the good news is that not only this is tractable, but the good news is that LP relaxation in this case is exact. So this class is solved exactly by this LP relaxation. And let me pinpoint the difference to what previous two speakers considered, that I assume that my variables have not only two states. They spoke about set functions, so it corresponds to variables with just two states, 0 or 1, whether it's in the set or not. But in this case, the variables can have a finite number, any finite number of states. So it's it's non-binary variables, but still finite, still discrete variables. So typical applications is computer vision, like image segmentation. We know already about that. But usually, so this LP relaxation is one way how to minimize these decomposable submodular functions. But more often, and more efficiently, submodular energies are minimized by reduction to maxflow algorithm in a graph. We've also heard about that. But this is fast, but it has drawbacks. First, this LP relaxation I spoke about is very nice in terms of the original graphical model, because, for example, reparameterizations, they keep the distribution the same. So it is something very, very beautiful and very natural. Whereas if you do this reduction to maxflow, you transform it to some other domain, then run maxflow algorithm to that, and then transform it back, and these maxflow algorithms has no simple relation to the original Gibbs distribution. So this is ugly in some way. And the other thing is that it applies, this reduction to maxflow applies only to limited settings, or to limited so to limited properties of the cost functions. For example, the arity can be at most 3. And now the contribution of this talk, of this poster, is a new class of algorithms, which we can poetically call a falling rain algorithms. And it has the following features. It directly solves the LP relaxation, but it can use only integer reparameterization, so we can use only integer arithmetics. It applies to any number of variables with any number of states and any order of the functions. Cost functions are accessed by oracles, so the oracle must return the minimum of the cost function plus some modular function, and it's a pseudo polynomial algorithm. Okay, so please come to our poster.
So come to the post-task, come and show the questions. And now we have a break for 15 minutes. So we reconvene.
I have a question. Thank you for your talk. What can you say about some additional constraint? What about when the power set H has a finite VC dimension? Could your algorithm can be faster in this case?
Okay, that set H was a hypergraph. That was a collection of the variable subsets. I don't know what you mean. I don't know what you mean by VC dimension of the hypergraph.
Probably this is a good question for discussion, and we can do it at the poster.
Okay.
Come to the poster.